In this session, we'd like to study the dynamical stabilities. So in the stability test, the response to small perturbations of the balance between the gravitational attraction and the outward force by the pressure gradient is compared. So in this dynamical stability test, we consider the radial perturbations. So this means compressions or expansion of a stars. If we apply the temporary contraction, if the star is going to expand, so in this situation is a dynamically stable stars. If the temporary contraction of the stars result in the further contraction and the contracting, so this means dynamically a star is unstable. So we'd like to study the dynamical stability of a stars. So as I explained, we'd like to consider the small radial compressions. So star is going to be compressed. So originally star has a radius of r. So this star is compressed. And the radius is changing r primes. So r prime and r is related. This one and the epsilon is a positive quantities. Because of that, this is gonna be the less than 1, r prime is smaller than r. So in this case, is a density is changing. So originally density is expressed m over r cubed. This is volumes. Then rho prime is expressed m. Total mass doesn't change. 4 pi over 3 r prime cube. You can substitute this r primes here. So it becomes m over 4 pi over 3 r cube 1 minus epsilon cube. Then this part is equal to the rho. So it becomes rho over 1 minus epsilon cube. So this is a relation between rho prime and the rho. I have explained. Then we'd like to consider the compression of a stars following the adiabatic contractions. There is no exchange of heat from the outside external world. It's the adiabatic contractions. So when we study the polytropic stars, pressure and density is related. The rho to the gamma. So from the disk, you can find that p prime over p is related to rho prime over rho. Then you can substitute this rho primes here. Then it becomes 1 over 1 minus epsilon, 3 gammas. This is approximated 1 plus 3 epsilon gammas. Pressures after the compressions and before the compression is related. P prime is equal to P times 1 plus 3 epsilon gammas. So pressure is increased by these factors. Then for hydrostatic equilibriums, pressure have to be balanced with the gravities. So that this is total mass of the stars. And if you consider the inner region of the stars, the mass is m. Then pressure gradient have to be balanced with the gravity. This is a pressure gradient. In the left hand side and the right hand side is a gravitational force. So from these equations, instead of r, if you use the m, round m, equal minus gm over 4 pi r to the fourth. We use a dm equal 4 pi r squares rho dr. So we use these relations here. Then we could integrate. This is m to the capital M, total mass, minus m to the m gm over 4 pi r to the fourth dm. And the left hand side, this is if you integrate pm minus pm. And the first term, this term is going to be 0 because the pressures become 0 at the surface of a stars. P sub m corresponding to the hydrostatic pressures. So from this equation, you can find hydrostatic pressure is equal to the integrals m to the capital M gm over 4 pi r to the fourth dm. Okay, this is hydrostatic pressures. So hydrostatic pressures is expressed this one in the before the compressions, and after the compression this r is changing to the r prime. So r prime is expressed, this is r to the fourth 1 minus epsilon to the fourth. So this is r to the fourth nearly 1 minus 4 epsilon. Then hydrostatic pressure is expressed P sub h, increase factor is 1 plus 4 epsilons. Condition for the dynamical stabilities. If the increased pressures P prime by the compression is larger than the hydrostatic pressures, then pressure is increasing, pressure is larger than the gravities, then the star is going to expand, return to the original state, restoring equilibriums. So in this situation it is stable. We'd like to find out the condition for the stable equilibriums. This condition can be expressed P prime, you can substitute P times 1 plus 3 epsilon gammas, and the hydrostatic equilibriums P times 1 plus 4 epsilon. So P is going to be cancelled out, and the P is going to be cancelled, and the epsilon is cancelled. So gamma have to be larger than the 4 over 3. This is the condition for dynamical stability. So dynamical instabilities. In the relativistic degenerate gas, gamma is a 4 over 3. Then the stars cannot satisfy the condition for the dynamical stabilities. In the case of the relativistic degenerate gas, U gas plus U sub radiation pressure is going to be minus omega. So in this case, total energy is a U sub gas plus U sub rad plus omega equal, you can substitute these relations here, it becomes 0. So relativistic degenerate gas, the stars composed of the relativistic degenerate gas, total energy is 0. So star is not bounded. So it becomes dynamically unstable. So this corresponds to the Chandrasekhar limiting mass. Stars with higher mass than the Chandrasekhar mass will contract and collapse. Then next nuclear reactions start. The star dominated radiation pressures. Also gamma is a 4 over 3. So in this case is also the E is 0, nearly 0. Star is unbounded. In this situation the star becomes dynamically unstable. Okay, this is the end of this session.